In this lecture, we'll discuss about CMOS circuits. Using CMOS circuits, we'll implement NOT gate, NAND gate, and NOR gates. These are the three basic gates for digital electronics operation. I'm not going to give you the detailed idea on CMOS because CMOS is widely covered in your electronics course. But before we start implementing these gates, let me give you some basic ideas how CMOS circuits operate. CMOS stands for complementary metal oxide semiconductor. We know the CMOS contains two types of MOSFET. One is NMOS and another is PMOS. That means N-channel MOSFET and P-channel MOSFET on a same substrate. That means it uses complementary and symmetrical parts of P-type and N-type MOSFETs for logic functions. Now MOSFETs are two types. One is P-channel MOSFET. Sometimes it is named as PMOS. And another is N-channel MOSFET. It is also named as NMOS. Now these MOSFETs can have two types of operations. One is switching operation that we are going to use for implementing these gates, and another is amplifier operation. Now let us see the symbol of N-channel MOSFET and P-channel MOSFETs. This is the symbol where this is named as gate. We have one terminal here, another terminal is here, and this is named as source and this is drain. And this voltage is named as VGS. Now in order to run this MOSFET in switching mode, we must provide VGS much more greater than the threshold voltage. So if we name the threshold voltage as VT, usually for this type of MOSFET, VT is 1 volt. So this is one reference value. Now if we provide VGS equals to 5 volt, that means this 5 volt is much more greater than 1 volt. So this will be in the saturation region. We can write saturation region. In saturation region, the current from drain to source or source to drain will be the highest, and we consider that this drain and source, they are shorted. So we can say we have drain terminal here, and this is the source terminal. This is a switch, and this is the gate voltage we are providing, which controls the switch. When we provide this gate voltage much more greater than the threshold voltage, it will move to saturation region, and that will cause this switch to be shorted. So this line will be shorted and current flowing through this line will be the highest when we are providing Vg equals to 5 volt. Now let us consider another condition when Vg or VGS is equal to 0 volt. When this gate voltage is 0 volt, that means this voltage is less than this threshold voltage, that means 1 voltage, much more less than this threshold voltage. We can have gate voltage 0 volt or minus 1 volt or minus 2 volt. So when the gate voltage is much less than the threshold voltage, then it will reach to the cutoff region. If we consider ID current in y-axis, and in x-axis we take VDS and ID in y-axis. When we take VG or VGS equals to 0 voltage, the curve looks like this. We can see the current flowing from ID to IS is almost equals to 0. That's why we say this region as cutoff region. Now as we increase the VGS, then the curve looks like this. This is for VGS equals to 0 voltage. When we are increasing the VGS, then this is VGS for 1 voltage. Then this is VGS equals to 2 voltage, for example. This is for VGS equals to 3 voltage. And suppose this is for VGS equals to 5 voltage. And this region is named as saturation region. So this is, we have saturation region. So when the switch is on, that means the switch is shorted. This is termed as switch is on. So when the switch is shorted or switch is on, this will operate in the saturation region. And when the switch is off, suppose we are providing VG equals to 0 volt, which is much more less than the threshold voltage, so it will stay in cutoff region. So ID equals to 0. ID equals to 0 means the current from ID to IS will be 0, and it happens when drain and source, they are not shorted or connected, and this happens when we are providing VG equals to 0 volt. And this condition is named as off condition. This condition is named as when the switch is shorted. This condition is named as on condition, and this condition is named as off condition. So we can say for NMOS or N channel MOSFET, if we provide VG 0 volt, let me write NMOS here, NMOS, and we will be doing for PMOS here, which will be opposite of NMOS. So when VG equals to 0 voltage, the NMOS will be off. And when we are providing VG equals to 5 voltage, the NMOS will be on. Similarly, if we see the symbol for PMOS, this is drain, this is source, this is gate. And we know from the PMOS characteristics, when gate voltage is 0, then PMOS becomes on. And when the gate voltage is 5 volt, then PMOS becomes off. So for the time being, this much knowledge on PMOS and NMOS is enough for implementing this NOT NAND and NOR gates employing CMOS circuits. Let us implement CMOS NOT gate or CMOS inverter circuit first. We know the NOT gate operation. If we have A input and if it is passed through the NOT gate, then the output F will be inverted value of A. That means if A equals to 0, that means logic 0, then F will be 1. If A equals to 1, then F will be 0. In other words, we can say if A equals to 5 volt, then F will be equals to 0 volt. And if A equals to 0 volt, then F will be equals to 5 volt. Now let us implement this inverter using CMOS. In the upper circuit, we'll be using PMOS, which will be connected with VDD. This is our source, and this is the drain. In PMOS, the current flows from source to drain, and this is the gate for PMOS. Then we'll be using another MOSFET, that is NMOS, and source side will be connected with ground. This is the source, and this drain will be connected with the drain of the PMOS, and this is the gate. Now we'll short this gate, and we'll say they are shorted. This is our input, and the output will be taken from here. Let us name this PMOS as Q1, and this NMOS as Q2. Now, how it operates. When we are providing input equals to 0 voltage, that means input we are giving 0 voltage, what will happen? The Q1, that is PMOS, and Q2, which is NMOS, we know when we'll provide 0 voltage to the gate of the PMOS, then PMOS will be on. And when we'll provide 0 voltage to the gate of the NMOS, then NMOS will be off. So this side will be short circuited and this side will be open circuited. When this source to drain, they are shorted, what will be the voltage in the output side? The output voltage will be 5 volt. So we can see when we are providing input equals to 0 voltage, this Q1 is on, Q2 is off, that means it is disconnected, and the output voltage will appear as VDD as because it is short circuited. So output voltage will be 5 volt if we provide VDD equals to 5 volt. Now when you are giving input equals to 5 volt, what will happen? When we are providing 5 volt in the gate side of the PMOS, then PMOS will be off. Off means this is open circuited, and NMOS will be on. On means this is short circuited. So this output will be connected with the ground, and we know this ground voltage is 0 volt, so the output will give us 0 volt. So we can see when we are providing in the input side 0 voltage, we are getting 5 voltage in the output side. When we are providing 5 voltage, we are getting 0 voltage in the output side. In other way, we can say this is acting as an inverter. When we are providing 0 here, we are getting 1 here. When we are providing 1 here, that means at the input side, then in the output side, we will get 0. One thing you need to remember while constructing any sort of gate, we generally use a basic construction. Suppose we have a VDD, then this VDD will be connected with PUN, that means pull up network, and this pull up network is generally made of PMOS. So this is pull up network. Then we'll be using PDN, that means pull down network, and this pull down network is generally made of NMOS. So this is PDN, and this PDN will be connected with the ground. Now this PAN will have, that means pull up network will have inputs. We may have multiple inputs, and pull down network that will also have multiple inputs, that may have multiple inputs. If we consider this structure and if we try to get the similarities between this circuit and this structure, we can say this is PMOS and this is pull up network, and this gate is connected with the input side. We have NMOS here, and this portion is pull down network, and the gate is connected with the input side. We have only one input, so only one input is here for this particular case, and output is taken from here. So for this case, the output will be taken from this terminal. This is output. So these are inputs, and this is output. Now let us design NAND gate using CMOS circuits. Now from our previous lectures, we know that the operation of NAND gate is very simple. This is the Boolean function expression of NAND gate. If one of the inputs or both the inputs are 0, then the output will be 1. For 0, 0, the output will be 1. For 0, 1, output will be 1. For 1, 0, output will be 1. For 1, 1, the ANDed output is 1 and the NAND output is 0. Now here we can see we have dot operation. If we have dot operation, let me tell you one shortcut method. If we have dot operation, Then you must connect the PMOS in parallel and NMOS in series. We know that PMOS will be used in PUN, that means pull-up network, and NMOS will be used in PDN, that means pull-down network cases. So let us design this NAND gate for two inputs, that means A and B. So if we have VDD, and as I said that PMOS will be connected in parallel, so let us consider the pull-up network first. We'll use two PMOS here. One is this will be taken from here. This is source and this is the drain. It's connected and we have gate here. This gate will be named as A input, and we need to connect another PMOS in parallel with this. So let me draw that, because PMOS are to be connected in parallel for this dot operation whenever we have this dot operation. So this will be connected like this, and this is B. So we have PMOS number 1, let's name it Q1, and this is Q2. Now this portion is the pull up network. Now we'll design the pull down network using NMOS, and the NMOSs are to be connected in series. So let us use first NMOS. We have this is the source side, and this is A, and another NMOS will be connected in series, and this side will be connected with the ground, and this is another input B. Let us name this as Q3 and Q4. The output will be taken from here, which is F. Now this portion is pull up network and this portion is pull down network. The pull up network is comprised of PMOS circuits and pull down network is comprised of NMOS circuits. Now let us draw the truth table. We have inputs A, B. Then we have four MOSFETs. They are Q1, Q2. This Q1 and Q2, they are PMOS. And we have Q3, Q4. This Q3 and Q4, they are NMOS. Finally, we have output. That is F. If we draw the truth table for different input cases, whenever A equals to 0, B equals to 0, what will happen? A equals to 0, B equals to 0. So whenever we are giving A0 and B0, PMOS will be on and NMOS will be off. So this PMOS will be on, this will be on, this will be off, and this will be off. So when they are on, these lines will be shorted and VDD will be appearing in the output side. So what will happen? The output voltage will be 5 voltage or VDD. So if we provide VDD equals to 5 voltage, we can directly write this is 5 voltage. Now whenever we'll give 0, 1, that means A equals to 0, B equals to 1. For 0, A will be on, that means Q1 will be on and Q2 will be off. Q3, as it is 0, this will be off, and Q4, as it is 1, because B equals to 1, so the gate voltage will be 1, so this is shorted, so this will be on. Even though this is shorted, as this is open, so the output will not be connected with the ground, but as Q1 is on, so this line is shorted, so output will be 5 volt. So we can write output will be 5 volt. Now when we are providing 1 0, then for 1 0 this Q1 will be off, Q2 will be on, this Q3 will be on, and Q4 will be off. So as one of the NMOS is off, so output will not be connected with ground. As one of the PMOS, that means Q2 is on, so this line is shorted, so output voltage will be 5 volt. So you can say output voltage will be 5 volt. Now for 1 1, what will happen? This Q1 and Q2 both will be off, and Q3 will be on, because we are providing high voltage here and high voltage here in the gate side. So for NMOS they will be shorted, and Q3 will be on and Q4 will be on. These two are off, so output will not be connected with VDD because they are off. PMOSs are off, and Q3 and Q4 they are shorted, so output will be connected to the ground. As ground voltage is 0 voltage, so for 1 case this will show us the 0 voltage. So in this way we can implement the NAND gate using CMOS circuits. Next we'll see the NOR gate implementation using CMOS circuits. We know the operation of NOR gates. For two input NOR gates, this is the function f equals to a or b whole prime. That means whenever we have both the input 0, then output will be 1. For all other cases, the output will be 0. In OR operation, you need to remember this method. Unlike the previous case, the PMOS will be connected in series and NMOS will be connected in parallel for OR operation. Here we have OR operation, and the total output will be inverted if we apply this method. We know the PMOS is used in PUN, that means pull-up network circuits, and NMOS is used in PDN, that means pull-down network circuits. Now let us construct the circuit. We have A or B whole prime. So first of all, we need to take VDD. As we have OR operation, so PMOS, they will be connected in series. This is PMOS. This is the gate, and we'll provide one of the inputs through this gate. Another PMOS will be here. This is connected here. We have gate here, B. They are connected in series, and this portion is the pull-up network. Now in pull-down network, we'll be using NMOS, as we have OR operation, so NMOS, they will be connected in series. Let us draw the NMOS. This NMOS will be connected in parallel. We need to just another NMOS, B, and this other side will be grounded. So let me mark this portion. This portion is our pull-up network, that means PUN, and this portion is our pull-down network, which means PDN, and the output will be taken from here. This is output. Now let us name the MOSFETs. This is Q1, this is Q2, this is Q3, and this is Q4. Now let's see the truth table for different input sets. We have inputs A, B, then we have Q1, Q2, they are PMOS, and Q3, Q4, they are NMOS and output F. Output which is denoted by F. So if we have 0, 0, 0, 0 means the PMOSes are getting 0, 0 at the gate input. So PMOS will be on, and NMOS will be off. And as they are off, both the PMOS are on. So the output will be equals to VDD. So VDD means, suppose we are having high voltage, that means 5 voltage. So we can say output will be 1. Now for 0, 1, what will happen? Q1 will be on, but Q2 will be off. As Q2 is off, that means this output is not connected with VDD. Then Q3 will be off, and Q4, as it is having 1, so this will be on. So the output will be connected with the ground through Q4. So the output will be 0 because the ground voltage is 0. Similarly, for 1, 0 case, this will be off, this will be on, this will be on, this will be off, and the output will be 0. For 1, 1 case, both these are off, this will be on and this will be on, and the output will be 0. So in this way, you can implement NOR gate using CMOS circuits. Next, we'll see the function implementation using CMOS circuits. Suppose we have this function f equals to ab plus b into c plus d. We will implement this function using CMOS circuits. We know the basic rule that if we have dot operation, that means AND operation, PMOSes are to be connected in parallel and NMOSes are to be connected in series. If we have OR operation, PMOSes are connected to be series, NMOSes are connected to be in parallel. If we apply this, we'll get the function in complemented form. From our previous section, we saw that. That means if we have A plus B, and if we apply this rule, we get A plus B whole prime. That means we implement NOR gate, or for the case of NAND gate, we get A dot B whole prime if we apply this rule. So after applying this rule, if we try to implement this function, we'll get f equals to ab plus b into c plus d whole prime. In order to get this function, that output should be sent through another NOT gate. That is the extra thing you need to do. Let us see how can we design this. Then the idea will be clear to all of you. Here we have 4 inputs, A, B, C, D. So we need to use 4 NMOS and 4 PMOS. First of all, let's implement this portion, AB part, in pull-up network. In pull-up network, we are going to use PMOSes. So whenever we have A dot B, that means dot operation, PMOSes are to be connected in parallel. So let's draw this. This is PMOS. We have A here, and another will be like this. This is B, and they are to be connected in parallel. Here we have VDD. So this AB portion is done for PUN, pull-up network part. Now still we need to complete this portion. We have B multiplied with C or D. So C or D, they are having OR operation. So for PMOS case, they are to be connected in series, and that should be paralleled with B, and this whole portion should be ORed with AB. That means ORed with AB means they will be connected in series. So let's complete the portion step by step. Let us do the C or D first. for C or D, we need to use two more PMOSes as they are having OR operation, so they are to be connected in series. So this is one CMOS, that is C, and connect another CMOS, that is D. They are connected in series C or D. Now the whole portion is ANDed with B. So whenever we have AND operation for PMOS case, they are to be connected in parallel. So we need to use another PMOS for B. This is for B, and they are to be connected in parallel with C or D. So this portion is C or D, and this portion is B multiplied with C or D. That is done. Now we need to OR this portion B into C or D with AB. So for OR operation, PMOSes are to be connected in series. So they are to be connected in series. So this is the PUN part, that means pull up network part. Now we'll go for the pull down network part. The output will be taken from here. This is the output part. In pull down network part, we will be using NMOS. Let's do the AB part. In AB part, for NMOS case, they are to be connected in series. So let us draw two NMOS in series. This is one NMOS and another NMOS. This is B. They are connected in series. So we have got AB here. Now for this portion, let us do the C or D part first. C or D, that means OR operation. For OR operation using NMOS case, we need to use parallel circuit. So let us draw here. This is NMOS. We are giving C here. Another one may be drawn here. We can say this is D, CD. As they are having OR operation for NMOS case, they will be connected in parallel. Once they are connected in parallel, we need to multiply B, that means AND. We need to have AND operation of B with C or D. This is the C or D part. For AND operation for NMOS case, the connection should be in series. So let us give another input, that is B in series. Now this is B into C plus D for pull down network. Now all this portion will be ORed with AB. So for OR operation for NMOS case, they will be connected in parallel. So in these should be connected in parallel with this AB part. And finally this portion will be grounded. And this output will be actually F prime. Now in order to get F, they must be sent through a NOT gate. So let's put a NOT gate here. We need to place a PMOS here. This is PMOS, and this should be connected with this VDD, and we need to give NMOS here. This will be grounded, and if we take the output from here, we'll get function. So in this way, we can implement this function using CMOS circuits. I hope you'll be able to solve any function using CMOS circuits if you understand this method. Up to this much today. Thank you.